All right, guys, we're going to take a little bit of time to talk about inverse functions today. Now, you already know kind of what an inverse is. Hopefully you did that back in your last class or last couple of classes, but just to kind of get the idea, an inverse is something that undoes another operation. So inverse operations would be things like plus and minus, right? Because if I start with x and then I add, let's just say 5, how do I get rid of that 5? Well, I subtract 5, and the plus 5 and the minus 5 cancel each other out, leaving me with x. Therefore, they're inverse operations. All right, same thing for multiplication and division, right? If I take x and I multiply it by 5, how do I get rid of that? Well, I divide by 5. When you're solving equations, that's what you're dealing with, is the inverse operations. They cancel each other out, therefore you're left with what you started with. So that's kind of the idea behind an inverse. Now, an inverse function is exactly that. We take some function, so f of x, which means that we put a number in for x, we do some function to it. It could be exponents, logarithms, addition, subtraction, multiplication, division, roots, all that kind of stuff. You do a whole bunch of stuff to x, and it gives you an output. Now, the inverse function, f inverse of x, will take the output and put it through the reverse process so that you end up with the same number that you started with. All right, so we'll look at a couple of examples later on, but that's the basic idea. Now, properties of inverse functions. Number one, they've got to be functions. Okay, which means that for each input to the inverse function, there can only be one output. Now, this leads us to the idea that the original function, f of x, must be 1 to 1. Because when 1 to 1 means that for each x value, there's only one y value, and for each y value, there's only one x value. Now, that doesn't have to be true for a function, right? A function, you could put different x values in and get the same y value out. You could have one y value that has several different x values, right? We see that all the time with quadratics, where two different x values go in and we get the same y value out. That's okay for a function. But if it's 1 to 1, that's not allowed. And I'll talk to you about that shortly, because we want to make sure that this is a function. Now, if we go through with that, we can now talk about the idea, what is another property of an inverse function? Well, if I do f, and then I do f inverse, this is how we write the inverse, with a little -1. Now, I know you learned back in Algebra 1 or something that the -1 means you move it to the bottom of the fraction. Well, that's the reciprocal function. The reciprocal function for a simple linear or simple exponential is that you move it down to the bottom. But -1 on the function actually means an inverse. And so we're going to go ahead and say if I do f of the f inverse, then it should take me back to x, right? If I do something to x, and then I do the inverse, then it should undo everything that was done. Now, it's exactly the same if I were to do the f inverse first of the f, then I should end up again getting x, because if I do the inverse and then I undo that, then I should end up ending with what I started from. Again, we'll look at this in just a minute. We'll look at maybe a couple of examples. So those are the basic ideas. The other major property of inverse functions is that it is reflected about the y equals x line. Okay, now this essentially means that all x and y values are going to flip-flop. Okay, anything that used to be an x will now be the output, and anything that used to be a y, that used to be the output, will now be the input. That's the whole idea, is that anything that you put in before can now go the opposite direction and go back to what you started with. All right, now that'll be important. Now what this results in is that the domain of f inverse will be equal to the range of the original function. Now that should make sense. Whatever y values used to work for a function are now the inputs for the inverse, because the x's and y switched. Now, the same thing is true if we say the range of f inverse is equal to the domain of the original function, because what used to be the x values of the original function are now the y values. All right, so that's kind of the theory about it. Hopefully that makes a little bit of sense. We'll show you a couple of examples right now. Okay, so here we go. Let's find an equation. Let's go ahead and leave these properties here because I think they're going to be helpful. All right, let's find an equation geometrically and algebraically for f inverse of x. Okay, so that's what we're looking for. All right, so first thing we're going to need to do is find out what the original function was. And so f of x, we can get the y-intercept. It's definitely linear, so it's going to be y equals mx plus b. So the slope is going to be, let's see, it looks like it's going up 2 over 1, right? Up 2 over 1, up 2 over 1. All right, so slope is 2, and then the y-intercept was 1. So 2x plus 1. Now, let's do this geometrically first. Let's look at the graph and see if we can do it that way. All right, now, we just talked about the fact that an inverse will be reflected about the y equals x line. So there's a couple ways to think about this, but let's go ahead and draw this y equals x line, which goes like this. I'm sorry that it's not very perfect, but here we go. Close enough. Okay, there we go. Oh, I messed up somewhere, didn't I? Oh well, that's life, isn't it? Okay, well, there we go. Oh, no, turned out. All right, so now I'm going to reflect it. Now what that means is that any point that's over here will now be reflected exactly on the other side. Now we said a result of that is that the x's and y's will switch. So for example, this point right here, which used to be 0, 1 for the original function, will now be 1, 0. I'm just switching the values, and so I'm going to put it right there. And you can see how that's being reflected across this red dashed line. So let's go to another point. This one used to be 1, 3. And so now it's going to be 3, 1. And so I'm going to go 3, 1, and there it is. And you can see how that's being nicely reflected across. Let's choose one on the other side. Let's go to this point down here, which was, oh, that's negative 2.5, negative 4. And so when I switch that, it's going to be negative 4, negative 2.5. And so I can put that down, negative 4, 2.5. There's the point right there. And so now I can draw this line, which will, let's go ahead and use a real line here. So we'll go from here, and then we need to go back up through this way, and then we'll kind of play with it to make sure that it actually looks like it's supposed to. All right, that looks pretty good right there. All right, so there's my line. And you can now see that this black one is a reflection of the purple one. Okay, now we've done that. Now let's go ahead and find the equation. So if I were to find an equation for this black line, right here is my y-intercept. So let's go f inverse. The slope is up 1 over 2, which interestingly enough is the reciprocal of that. And then let's see, the y-intercept is negative 1/2, so minus 1/2. So there you go. There we did it geometrically. Now let's do it algebraically. Algebraically, we're going to do exactly the same thing, except instead of flipping individual points, we're just going to go ahead and switch the whole x, y. So instead of y equals 2x plus 1, we're now going to change it so that x equals 2y plus 1. Now we can solve for y. So let's go minus 1. So I've got x minus 1 equals 2y. I'm going to divide by 2, so now I've got, this was a 1x, so that's 1/2 x, minus 2 divided by 2, which is 1, and, so, oh, sorry, holy smokes, how did I do that? I subtracted a 1 and ended up with a 2, didn't I? Okay, there we go. So negative 1/2 equals y. And so there we got the same equation that we started with. All right, then we can look at f of negative 1. So if this is really the inverse, we should be able to do f of f inverse, and it should get rid of everything. So let's take the original function, and let's put f inverse inside. All right, so that's 2 times x, but instead of x, we're going to put f inverse. So 1/2 x minus 1/2, and then plus 1. And so if we do that, we should get, if I distribute the 2 to both of these, I get 2 times 1/2, which is 1x, and 2 times negative 1/2, which is -1. And then I still got the plus 1 over there, and you'll notice these cancel out, which leaves us with x, which then shows this idea of the fact that the f of the f inverse should be x. All right, I think that's enough for this video. Go on to the next one, and I'll try to do one other example for you. Ciao.